Okay. So we will see space vector modulation. Okay. So before that, I will give an intro regarding the space vector modulation. Why we are going for this space vector modulation? Okay. So first of all, I will draw one block. So you are having a V reference will be there. So you will be having a reference voltage will be there. So you can have a reference voltage, and this reference voltage that has to be fed to a PWM generator. So definitely this reference voltage is given to a pulse width modulation technique. So you will be having a PWM, pulse width modulation. And this pulse width modulation that has to be given to a voltage source inverter. So you will be having a voltage source inverter will be there, VSI. So that is voltage source inverter. And this voltage source inverter will be giving the sufficient input to the motor. If you want, you can draw it like this. You can have a motor like this. Okay. So you'll be having a motor will be there. Motor will be there. Okay. So you have, our ultimate aim is to develop the reference voltage. So you'll be having a PWM in the voltage source inverter. As you know, you are having different switches will be there. Power semiconductor switches will be there. You can have IGBT, MOSFET, and anything can be there. So in the voltage source inverter, why we are calling this voltage source inverter is the input corresponding to that will be a DC voltage. And the output corresponding to that voltage source inverter should be always an AC voltage. And that will be used to drive the particular motor. If you want to connect any load to this motor, pump or anything, you can have that also. Okay. So if you are having a current source inverter means that will be having a current source as the input, and you will be getting a AC current waveform that will be driving the sub motor or any load connected to that one. So in the voltage source inverter, always the impedance will be, input impedance will be less. But in the current source inverter, the input impedance will be more. So we are here we are referring the voltage source inverter. So since the voltage source inverter will be having the power semiconductor switches, anyway you have to give the pulses corresponding to the switch bar. So for that we are using the pulse width modulation technique. So this space vector modulation, it is just an algorithm for the control of pulse width modulation. So we can say this is nothing but an algorithm used for, this is an algorithm used for the control of pulse width modulation. Okay, pulse width modulation. So it is mainly used for, as I told you, it is mainly used for the creation of alternating current waveforms. Anyway, the input corresponding to the machine will be an AC. So what you have to do is you have to generate this AC waveform, the output of this one. So this has to create alternating current waveform. So alternating current waveform. Alternating current waveform. Okay, create alternating current waveforms. So why we are creating this alternating current waveform is to drive the three-phase AC powered motor. So in order to drive the three-phase AC powered, remember the term AC powered motors at varying speed. Okay, so you have a PWM is there, then you have the voltage source inverter is there. The input to the voltage source inverter will be always a DC, and you have to generate an AC, and this AC waveform will be having a sinusoidal in nature, and that is mainly to drive the three-phase AC powered motors connected to the voltage source inverter. So suppose if you are having a three-phase balanced voltage in a three-phase, if you are providing a three-phase balanced voltage to the three-phase induction motor, and they are definitely, since it is a three-phase system, they will be sinusoidally varying functions, and that will be displaced at an angle of 120 degrees. Suppose if you are taking a three-phase system, you will be having A phase will be there, then you will be having a B phase will be there, three-phase system, B phase will be there, then you will be having a C phase will be there. So these all the phases will be displaced at an angle of 120 degree. So we will see this will be displaced at an angle of 120 degree. Okay. So you will be having this one. So this is your C. See, this one will be displaced at an angle of 120. So here this will be displaced at an angle of 120. Again, this B and C will be displaced at an angle of 120. So 120 phase shift will be there. And this will be displaced at an angle of 120 degree. Okay. So each will be, if you are having a three-phase balanced voltage that is applied to a three-phase induction motor, then these phase voltages will be sinusoidally varying functions. As you can see, it will be sinusoidally varying functions. So if it is like this, at 120 degree, you will be having the another waveform, and then at 240 degree, again, you will be having the another phase will be there. Okay. So the three phases will be varying with respect to the phase angle, that is 120 degree. And this three-phase phase vectors add up to give a resultant phase vector. So you are having a three-phase system. This three-phase system will definitely add up to give a resultant space vector. So you will be having a resultant space vector will be there, right? So a resultant space vector will be there. A resultant space vector will be there. So this resultant space vector will be having constant amplitude and it will be rotating in space at a constant angular speed. So this resultant space vector, if you are adding the three space vectors, you will be getting a resultant space vector, and this resultant space vector will be having a constant amplitude, which is rotating at constant angular speed, constant angular speed. Okay, constant angular speed. So this is the concept which is analogous to the space vector modulation also. Anyway, you have to develop a resultant space vector that has to be rotate at constant angular speed, and it will be having a constant amplitude. So we have to treat the sinusoidal voltage as a constant amplitude vector rotating at constant frequency. That is the basic concept associated with the space vector modulation. So the PWM controller, as in the diagram shown there, you are having a V reference will be there. Then that is fed to the PWM generator. Then that is again given to the voltage source inverter. Then that has to be used to drive the motor. So this PWM controller is commonly used to get the sinusoidal current distribution. So why you are having the sinusoidal current distribution is in order to get a continuous power flow. So in order to get a continuous power flow, always you should have a sinusoidal distribution. So this SVM treats the sinusoidal voltage as a constant amplitude. So this thing you have to be very careful, because it will be having a constant amplitude and it will be rotating at constant angular frequency. So this SVM modulation technique that mainly calculates the duty cycles of the switches. So it calculates the duty cycle of the switches. In order to get the desired output voltage on an average basis without the use of a carrier waveform. So if you are comparing with a sinusoidal pulse width modulation, there we are using the control signal will be there, then you will be having a carrier signal will be there, definitely you will be having a control signal will be there, then you will be having the carrier signal will be there. So then you will be taking the different pulse ranges will be there. Okay, so you can take that in that way. But in the case of space vector modulation, this will always calculate the duty cycle of the switches to synthesize a desired output voltage on an average basis. Next, then we will see how this voltage vector or the reference voltage vector can be generated. Okay, so then moving on to the construction part. So in the construction part, you will be having this voltage. I am drawing the voltage source inverter. So you will be having a DC source voltage will be there. Then if you are having a two-level inverter, definitely you will be having six switches will be there. So you can have 6 switches. As you can see, So I'm drawing the structure, and definitely it is a bidirectional switch. So bidirectional switch in the sense, once you will be having the switch is on means this will be continuing this path, and the another way, if it is goes to the source means it will be using this path through the diode path. Okay. So here you will be having a diode combination is also here. Okay. So then again you will, this is corresponding to first leg. So I am drawing the second leg also. Second leg. So you'll be having this structure, and again so the third leg. Okay, third leg. So as you can see here, you will be having, this is the VDC. Here you will be having two levels will be there, either 0 or VDC will be there. Or if you want, you can split that also. If you want, you can have a midpoint like this, and then you can take the 0 point here. Then again, you can provide this one. At that time, you will be getting VDC by 2, and you will be getting the bottom part, you will be getting minus VDC by 2. So you will be having again two state will be there, plus VDC by 2 and minus VDC by 2. If you are having only one structure, this is the middle point corresponding to this one. So that means you can have like this. So if you are having this only VDC is there, you will be having two state will be there, that is 0 or VDC. Okay. And again, from here you will be having one point that is known as the pole point. So you can take one point from the first leg. So first leg you can take one point. And in the second leg also you can take another line, and then the third leg also you can have another line. Okay. So here you will be having this corresponding to capital A, this corresponding to capital B, midpoint corresponding to this one, this is capital C. So this has to be connected to the motor part. This has to be connected to the motor part. Okay. Or in any other load, if you want, you can have, if you want to modify this one, you can definitely have an inductance, then you can have a resistance will be there, then you can provide the back EMF corresponding to this one. This will be the representation corresponding to the per phase. You can have a resistance, you can have an inductance, you can have a back EMF corresponding to first phase. The similar way you will be having a resistance, you will be having an inductance, then the back EMF corresponding to second phase also you can take. So this motor, if you want to expand, you can have like this. So you can have like this structure also easy. This is also possible. But I am simply drawing like, since you are having a motor part only. So you are having a VDC is there. As you can see, this will be forming your first leg. This is your second leg, and this is your third leg. So how we can mark this one? This is your S1, and this is your S3, and this is your S5. Okay, top switches. And then you will be having, this is your, what about this one? S4, then you will be having S6, then you will be having S2. S2. Okay. So you can have three legs will be there, as you can see here, or three legs, or we can call it as three poles will be there. So either you can say three leg, or you can say three pole will be there. Three leg, or you can say three pole will be there. Then how will you identify whether you are having, how many states are possible for this particular inverter? So you are having a VDC is there, then you are having the inverter switches are there, then that is connected to the motor part. Then you are having three leg, or you can have three poles, A, B, C, three poles are there. But in the case of a switch, it is either on or off condition is possible, right? Either it can be on or it can be in the off condition. So on means you are having 1 and off means you are having 0. So in this switch will be having only two possible conditions, that is 1 or 0 combination. So how many states will be there for this total? How many states will be possible for this circuit? So since it is a bidirectional circuit in the sense, if you are having the power flow will be from the source to the load means that will be flowing from this one. Then if the switch is on means through this path, this will be completing and then it will be goes to the motor. And suppose if the power flow is from the load to the source, then definitely this will be flowing like this and this will be taking the diode path and it will be completing the path like this one. So that is the, here also you will be having. So that is the concept regarding this one. So here how many states will be there? So you will be having a top pole switches are there. As you can see, this is the top pole switches and this is the bottom pole switches. Each will be having either 1 or 0 state. Okay, 2 state is possible. Either it can be 1 or 0. Then since you are having 3 poles or the 3 legs are there, you can have 2 raised to 3 combinations possible. So 2 raised to 3 combination means 8 state can be possible. So this is most important one. 8 state can be possible. Why? Because you are having 2 state is there, either 1 or 0. But you are having 3 leg or the 3 poles. This will be forming 1 leg. This is another leg. This is another leg. So you can have a 3 leg or a 3 pole structure. So in effect, you will be having 2 raised to 3 states is possible. So 2 raised to 3 means 8 state is possible in the case of this circuit. So how we can write this state? So if you are taking the states possible are, if you are taking the states, then you will be having, if you are taking A, then you can take B, then you can take C. So first it is possible if you are having this, all the bottom switches are in the on condition, then you can have 0, 0, 0. Why? Because when the bottom switch on means, you will be having bottom switch on condition means you will be having 0 representation. If the top switch on means, that indicates 1. So if the top switch on means that indicates 1. If the bottom switch on means that indicates 0. So you can have, if all the bottom switches are 0, or simply if I am drawing like this one, just to have this. Okay, I will draw like this. Okay, so you'll be having the first leg. Then for simplification, I am drawing like this. You will be having the second leg, and then you will be having the third leg. Then you will be having a load connected to this one, that is simply a motor. Okay, so here if all the bottom switches are on means this will be in the closed condition, right? It will be in the closed condition, or we can write this will be equal to 0, 0, 0 condition, because when the bottom switches are on, that indicates by 0. So you will be getting 0, 0. And suppose if you are having only 0, 0, 1, what it implies? If you are having 0, 0, 1, so what it represents? 0, 0, 1 means the C will be on, right? So A, B, C, you are having this is A, this is B, and C will be there. That we will see. C. And another combination possible is you can have either 0, 1, 0 is possible, or you can have 0, 1, 1 is possible, or you can have 1, 0, 0 is possible, or you can have 1, 0, 1 is possible, or you can have 1, 1, 0 is possible, or you can have 1, 1, 1 is possible. Okay, 1, 1, 1 is possible. So these are the 8 states corresponding to the space vector modulation. So you will be having 1, 1, 1. Okay, so this will be 1, 1, 1. So as you can see, this state, that is 0, 0, 0. So the 0, 0, 0 means the bottom switches are, all the bottom switches are in the on condition. So the 1, 1, 1 means all the top switches are connected to the top rail, or we can say that is switched on. So these two states, you can see 0, 0, 0 and 1, 1, 0. So all the top switches are on, or all the bottom switches are on. Suppose if all the top switches are on means what will happen? It will be shorted. And all the bottom switches are on means here also the bottom part will be shorted. So this condition is known as the redundant condition, or we can call that state as 0 state, because it will not contribute towards the non-zero output voltage. So it will not have any effect on the output voltage. Okay, so we can call this as the 0 state. Why we are calling this as the 0 state means, because if the top switches are on or the bottom switches are on, that will short circuit this system, and it will not contribute to the desired output voltage. So we can call this as a zero state. So this is known as the zero state, and this is also known as the zero state because it will not contribute anything to the output voltage. So this is your zero state. Again, so you have two zero states are there. That is, either you can have this bottom switches on, or you can have the top switches on. So if that means this poles are, if the top switches are on, means the poles are shorted to the poles are shorted, A, B, C are shorted to the top part. If the bottom switches are on, means 0, 0, 0 combination. So the poles are shorted to the bottom. So you have two conditions are there. Either the poles can be shorted to the top rail, or the poles can be shorted to the bottom rail. So these two states are known as the zero state. And you are having how many of them here? So you are having 6 another states are there. So these 6 states are known as the active state. So you have active vector state or active state. So in the case of space vector modulation, you are mainly having 2 zero state. The 2 zero state means you are having either the bottom switches shorted and it is connected to the bottom rail, or you can have the top switches will be shorted and that will be connected to the top rail. So these two conditions are known as the redundant condition or the zero state condition, and the rest will be your active state. So the active states are either 001, 010, 011, 100, 101 and 110. So these are the different state combinations possible in the case of a space vector modulation. So next we will see how these switches can be connected. So these are the state, right? So if this is the state, if you are representing this one, so I will draw the circuit. Suppose if you are having, you can also draw for the other circuits also. First one I will explain, and this next one you can randomly choose and you can draw it along with me. Okay. So if you are having this one, this will be representing A pole, this will be representing B pole, this will be representing C pole, or we can say this is the first leg, second leg and third leg, or the first pole, second pole and third pole. So here, if I am writing, this is simply 100, how I will represent this one, 100. If I am representing 100, how will I represent it in the diagram? So if it is 100, how will I represent it in the diagram? 1 means this is your A part, right? This is your B, this is your C. So A switch will be in the on condition, right? So you can have this one as the on condition of A. This is your A connected to A pole. Okay. Then the next one is 0. So 0 means you will be having this B pole will be connected to the second leg. That is in the bottom. Bottom switch on means that is representing 0, indicating 0. Top switch on means that is indicating 1. So here the top switch is only A will be connected to the first leg, right? So you are having this pole will be connected to here. Here you will be having, it will be connected to this pole. And what about C? C also the bottom switch, because the bottom switch on means that will be indicated by 0. So the bottom switch C will be, the pole C will be connected to this switch part. So this will be a combination corresponding to 100. So can anyone draw for 110 if I am having 110? What it implies, you are having A switch is in the top switch, that is on, B switch in the top part, that is also on, C switch is in the bottom part, that is also on. So how we can represent this one? Can anyone draw it? Anyone? And you can switch on your audio and you can say which one, anyone. So which one will be representing the top switch part? Which one will be representing the bottom switch part? Can anyone? Nobody? Okay, fine. So the top switch one means you will be having this as your A. This is your top switch because this is the top part switch. So that is A, that is connected to A. Fine. Then what about the bottom here? B part. B part is also 1. 1 represents means the top switch will be 1. Again, it will be connected to the next pole B. What about the C part? C part means the bottom switch will be 1. That's the, if the bottom switch 1 means that is indicated by 0. So definitely you will be having C will be connected to like the bottom part and that will be connected like this. So this will be the indication corresponding to 110 switch position. Then how we can represent 010? I will draw all the parts. So 010. Suppose if you are having 010 is definitely A bottom part, B top switch, C bottom part will be there. So if you are having this structure, this is a simple structure I am adopting for this for the analysis. So you are having ABC. So here, how you are having 3 poles will be there. 3 poles means you are having A, then you will be having B, then you will be having C. So if you are having ABC structure, this 0 represents what? 0 will be representing your what? Bottom switch, right? So you have to always connect to the bottom part. So this will be your A, connected to the A pole part. Then what about your 1 switch? 1 means B will be 1. So definitely B will be in the top part. So you will be having B part. Okay. And then what about your C part? C is again in the bottom part. So this is representing C. This is your 0, 1, 0 combination. Can anyone draw for 0, 1, 1? 0, 1, 1? All the combinations, if possible, you can draw it. If you are correct or if you are confident, then it's good. Else, you can just copy it down. So here you will be having 0, 1, 1. So 0 means again you will be having A, this is B, and this is C. So our assumption is if you are having 0 means the bottom switch will be 1. So 0, 1, 1 means you will be having this one. So this represents your 0 part, that is A connected to the A pole. And B and C are 1. So B and C are 1 means you will be having the top switch will be in the 1 position and that will be connected to the pole B. And here also the top switch will be 1 and that will be connected to the C pole, right? So if you are having 0, 0, 1, if you are having 0, 0, 1, how we can mark these points? If you are having 0, 0, 1 means, if you are having 0, 0, 1 means, you will be having see 0, 0, 1, 0, 0, 1. As you can see, you are having A, B, C will be there. So A is 0. So A is 0 means definitely what you will be getting? The bottom part. That will be connected to A pole. And B is also bottom part that is connected to the B pole. What about C pole? C pole will be connected to the top. So you will be getting C. This is corresponding to your 0, 0, 1. Then what about your 1, 0, 1? So all the 6 active vectors I have drawn, 1, 2, 3, 4, 5, 6. So all the 6 active vectors, how the combination coming? So just you can copy it down. So 1, 0, 1. So if you are having 1, 0, 1, 1 means the top switch will be 1. So you can definitely have a top switch 1 that is connected to the pole A. And then you will be having 0 is there. So 0 means definitely the B will be the bottom switch. So you can have B representation. And again, you will be having a C that will be the top switch. So you can represent like this one. So this is 1, this is 0, this is 1. So this is the combination corresponding to this one. And suppose if I am drawing this 0 vector, because 2 redundant states are there, that will not contribute to the output voltage. So the 2 0 state vectors are inverter states are there. So how we can draw this inverter state? So again, you will be having 2 combinations. So first combination is if you are taking it as 1, 1, 1. So if you are having 1, 1, 1, that is both A, B, C are 1, 1, 1. So how we can represent this one? So 1, 1, 1 means you will be having, this will be connected to A phase, this will be connected to B pole, this will be connected to C pole. So you are having, this is your A, this is your B, and this is your C. This will be a shorter condition, okay? And then again, if you are having 0, 0, 0, so that state can be, you can have the bottom part will be shortened. So here, if you are having this much, then you can have, this will be, you are having A part will be connected to pole A. This is your A, this is B, and this is C. This is your 0 state. This is shorted to the bottom right. So these are the inverter states corresponding to a space vector modulation. So you are having 6 active vectors and 2 0 vectors will be there in the inverter switching state condition. So next I will the resultant vector. So you have to draw the hexagonal construction. So how you can generate the reference voltage that we are going to see. So in that part, you will be having, as I have already drawn the circuit, that is, I'm sorry, I will take the pen. Okay. So you are having a DC voltage will be there. Then this DC voltage, you will be having this 2 combinations, first leg, and then you will be having the second leg representing the second switch and the top switch and the bottom switches. Okay, just I am drawing like this. So this is your A pole. As you can see, this is your A pole, this is your B pole, and this is your C pole, and this is your VDC, right? VDC. Then if you are analyzing, this is the construction of hexagon, or we can call it as the resultant corresponding to this all the switching states you have to obtain it as a hexagon shape. So how is it possible? So if you are having 1 0 0, I am taking all the combinations 1 0 0. I am taking 1 0 0. Okay. If I am taking 1 0 0, okay, 1 0 0, 1 0 0. So the resultant of 1 0 will be what? So anyway, you will be having a three-phase quantity. So the three-phase quantities will be we can return as equal to, if you are having VA, that can be represented as equal to, this is a sinusoidal quantity. So you are having a Vmax sin omega t will be there for the first one, A phase. And if you are having B phase, that will be having Vmax, but it will be displaced from the A. If you are taking A as the reference, then it will be having Vmax sin omega t minus 120 degree, because these two are displaced at an angle of 120 degree. If you are having the C combination, then you will be having Vmax sin omega t minus 240. Minus 240. Why? If you are taking the reference as A, then you will be having A phase, then you will be having B phase, then you will be having C phase. So if you are taking the reference as A, then you will be getting it as equal to A, B, C. This will be Vmax sin omega t. This will be Vmax sin omega t minus 120. This will be Vmax sin omega t minus 240. You have to consider the whole angle. Okay. And here also, if you are considering 1 0 0 state, you have to find out the resultant of 1 0 0. Okay. So the resultant of 1 0 is A is the top switch, B and C are the bottom switches, right? So you have to draw the three switch patterns because it is a three-phase system. So you can draw, this is your A phase, and this is your B phase, and this is your C phase. C phase. Okay, C phase. Then, so A is turned on, right? 1. So A is turned on means you will be getting the pole voltage with respect to the bottom part. You will be getting the pole voltage with respect to the bottom part. And A is now at plus VDC level and B is at 0 level, because B is with respect to the bottom level means you will be getting it as the ground position. So you will be getting 0. If A is with respect to the top level means you will be getting plus VDC. So two combinations are there. If top switches are on, you will be getting it as plus VDC level. Then, so we will see you are having ABC that's equal to 1 0 0. 1 0 0 in the sense A is at plus VDC level, B is at 0 volt and C is at 0 volt. So anyway, you have to get the resultant vector. So how will you get the resultant vector? These two are at 0 volt, definitely. So if you are taking the resultant corresponding to these two, again you will be getting it as 0. Then plus you are having this VDC level. So you will be getting a vector that will be in this direction. See, one vector in this direction, I have marked like this, that is corresponding to 1 0 0. Okay, fine. Then I have to mark for 1 1 0. How you will get? Why I am taking this 1 0 0 concept means, if I am having 1 0 0 here, the first A switch is in the on condition. That's why I have taken 1 0 0 level. Okay. So 1 0 0 in the sense, first A switch will be in the on condition. So you are having 1 0 0 level. So then if I am taking 1 1 0, what will happen? If I am taking 1 1 0 condition, so you have to draw it in the same way and you have to find out the resultant corresponding to this one. So if you are having 1 1 0, if you are having 1 1 0, 1 1 0, then you have to draw the same thing. So you are having A phase because all the phases are displaced at an angle of 120 degree. Definitely you will be having A phase. Then you will be having at 120 degree, you will be having B phase, 120 degree. Then at 120 degree again, you will be having C phase will be there. Okay. Then you have to draw the resultant corresponding to this 1 1 0 because A switch is on and B switch is on and the C will be 0 state will be there. So how will you draw this one? How will you draw this one? So A is at plus VDC, right? So you can mark A is at plus VDC. Fine. A is at plus VDC because this is A, this is B, this is C. So as we can see, A is at plus VDC, B is at plus VDC because it is top switch is on, and C is at 0 volt level. Okay, 0 volt level. So you have A as plus VDC. I am marking it here. So this is plus VDC level, fine, plus VDC. And B is also at plus VDC level. This is also at plus VDC level. Okay. Then you have to take the resultant corresponding to this one. So if you are taking the resultant corresponding to these two, definitely you will be getting a resultant that will be passing through the origin like this, because it will be just the inverse of the C phase. Okay, it will be just the inverse of the C phase. As you can see, this will be just the inverse of the C phase. So it will be just the inverse of the C phase. Okay, so this is your C phase. As you can see, this is the inverse of the C phase. So the resultant will be always the inverse of C. Or you can say A plus B will be equal to what? Minus C. So how you are getting that A plus B is equal to minus C? So remember, in the case of a balanced three-phase system, in the case of a balanced three-phase system, in the sense all the impedances corresponding to that will be the same. If you are having A phase impedance is the same as that of the B phase impedance, and that is the same as that of the C phase impedance. So if all the impedance of the phases are same, then you can say it as the balanced three-phase system. So in a balanced three-phase system, always the current IA plus IB plus IC, that is the triplet current, will be always equal to 0. Or you can say, if you are taking IA plus IB, you will be getting minus IC. The same concept is applying here also. Or if you are taking voltage, you will be getting VA plus you can say VB plus you can say VC, that will be equal to 0. So you can say either if you are taking the two phases, then it is sufficient, because in the case of a balanced three-phase system. So here you are getting it as a resultant corresponding to this will be in this direction, that is VDC. The resultant corresponding to this will be VDC. Okay, VDC. So we can mark here as equal to VDC. So the second vector, that is the second voltage vector, I am getting it as equal to corresponding to 1 on 0 is, this is corresponding to 1 on 0 is in this way. Okay. Wait a minute. Savitha, I am invited talk. I am going to villachola. Okay. Okay, so you will be having 1 on 0. So 1 on 0 in the sense you will be getting this vector in this direction, right? So you can mark here another vector that will be in this direction. Okay, so this is 1 on 0. I am marking like this. See, 1 on 0. And now I am moving on to 0 on 0. If I am having 0 on 0, how I will mark like this? So you are having an A phase will be there, and you will be having a B phase will be there. Then you will be having a C phase will be there. So this represents C, this represents B, and this represents A. So again, you will be having, as you can see, A phase you will be having, this is A, this is B, and this is C. Only B is at plus VDC level, A and C are at 0 level. So how you will be getting, only in this direction you will be getting the plus VDC, right? Only this is your vector, the voltage vector representing in the B direction, that is equal to VDC. This will be representing 0, 1, 0. So again, you will be getting another vector, and that vector will be in the B direction. So this is your B direction. So you will be getting 1, 0, 1, 0, right? 0, 1, 0 will be there. So you have that this is the A phase corresponding, this is the B phase corresponding, and next you have to move on to 0, 1, 1. So how you will be getting the resultant vector? So this is the resultant vector corresponding to this one. And suppose if you are moving on to the 0, 1, 1. Can anyone draw 0, 1, 1? How you are getting that voltage vector 0, 1, 1? Can anybody say 0, 1, 1 means A is at 0 volt, B and C are at? So you are having 0, 1, 1, right? Yeah, 0, 1, 1. So 0, 1, 1 means this is A, this is B, and this is C, A, B, C. So if you are having A, B, C, then definitely the A is at 0 volt, B is at plus VDC, C is at plus VDC. So our diagram will be, this is A representation, this is your B representation, and this is your C representation. So we can see this A is at 0, doesn't matter. But B and C are at plus VDC level. So if B and C are at plus VDC level, you will be getting the 2 VDC will be there. You have to take the resultant corresponding to these two, Definitely this will be passing to the through the origin like this. This will be just inverse of this one, because for a balanced system, you are always getting it as equal to IA plus IB plus IC, or we can say A plus B will be equal to minus C. The same concept here you can apply, that is B plus C will be equal to minus A. That is the same. So here also you are having this is equal to A plus B will be equal to minus C. A plus B will equal to minus C. Same concept you can apply here also. So you will be getting another vector that will be having a VDC level. So that is in this negative direction of A. So you can have another vector, voltage vector, that will be along this direction. See, along this direction. And that will be representing your 0, 1, 1. Okay, 0, 1, 1, 1, 1. Then how you can represent your 0, 0, 1? So the another way representing 0, 0, 1. Can anyone represent 0, 0, 1? 0, 0, 1. Can anyone represent 0, 0, 1? You are having ABC structure is there. Then can anyone draw the 0, 0, 1? So 0, 0, 1 means if you are having
0, 0, 1 will have A and B as
somebody is telling.
In 0, 0, 1, A and B will have
It will
0
be
volt.
C, right? It will be through the C. Yeah. Very good, very good. Okay. So next I will be moving on to very good. 0, 0, 1. So 0, 0, 1 means the resultant you have to obtain. So we can see this A is at 0 volt, B is at 0 volt, but C is only having the voltage plus VDC. So how we can represent that one? You are having A phase, you are having B phase, then you are having C phase, right? A, B, C phase. A, B, C phase will be there. But you are having 0, 0, 1, right? So 0, 0, 1 means this A is 0. So definitely this will be 0. B is 0. Definitely here. But C will be having a plus VDC level. So the C will be having a plus VDC level, and that is your 0, 0, 1. Or here you can mark, this is your C phase, just the reverse of this one. So this will be representing your 0, 0, 1. See, 0, 0, 1. Next, I have to move on to 1, 0, 1. Can anyone say how this representation, how you can draw this representation corresponding to this one? See. So next one, I am moving on to 1, 0, 1. Okay, right? So 1, 0, 1. So if you are having 1, 0, 1, the same manner you can draw. That's A, then you can have B, then you can have C. Okay, you can have C. 1, 0, 1 in the sense 1 is A is 1, B is 0, C is 1. So A is definitely you will be having what? Plus VDC level. B is at 0 level, so 0 voltage level. C is again at plus VDC level. So the A and C are at plus VDC level. So if you are having A and B at plus VDC level, this is your VDC level. This is also a VDC level. A and C are at VDC level. Then you have to construct a parallelogram, and you will be getting the resultant diagonal corresponding to that parallelogram will give you the resultant vector. So here you will be getting just reverse of B. Why? Because A plus C you will be getting for a balanced system that is equal to minus B. So you will be getting along the negative direction, you will be getting the resultant vector. So you can draw here, this is your B, and this B vector you can draw like this, and you can draw like this. Okay. So this will be representing your what? This will be representing your 1, 0, 1. 1, 0, 1. So if you are getting this vectors, 6 voltage vectors are there, right? 6 voltage vectors are there. But you are having 2 0 states are there. So how we can represent that 0 states? So you are having a 0 state is also there, right? So you have to represent that 0 state also. So in order to represent that 0 state, you will be having what? Either you will be having 1, 1, 1, or you will be having 0, 0, 0, right? So if you are having 1, 1, 1, if you are having 1, 1, 1, let's see, 1, 1, 1. So if you are having 1, 1, 1, what it implies? A is at plus VDC, B is at plus VDC, C is at plus VDC. Then what you will be getting? If A is at plus VDC, as you can see here, A, then you will be having B, then you will be having C. So A, B, and C. If A is set plus VDC and B is set plus VDC and C is set plus VDC, you have to take the resultant corresponding to these two, because if you are taking this one, you will be getting the resultant corresponding to this will be construct a parallelogram and take the diagonal corresponding to this one. This will be just a reverse of this one. So you will be getting the resultant corresponding to VAB. Then that resultant will be just opposite, that is equal to minus VC. Or if you are taking the resultant corresponding to these two, again you will be getting a 0 voltage, because it will not contribute to the desired voltage. So finally you will be getting the resultant of A and B. First of all you have to take, because A is at VDC, B is at VDC, C is at VDC. So first of all you have to take the resultant corresponding to A and B. The resultant corresponding to A and B is minus C. Then you have to take the resultant corresponding to minus C and C. So minus C and C, resultant corresponding to these two will be equal and opposite. So definitely you will be getting a 0 volt. So here you will be getting 0 volt. Then what about for the 0, 0, 0? Definitely, because A will be 0, B will be 0, and C will be 0. That is at circle. So here you will be getting 2 points, 0 state vectors will be there. So that 0 state vectors are either you can have 1, 1, 1 structure, or you can have 0, 0, 0 structure. So all the 8 states I have written here. So you can have 1, 1, 1, 0, 0, 0, then 1, 0, 0, 1, 1, 0, 0, 1, 0, all these things are there. If you are joining all these voltage vectors, so now we have 8 vectors will be there, 6 active vectors and 2 0 state vectors. Suppose if you are joining all these, or if you are combining all the voltage vectors, you can draw a hexagon. So this hexagon is the main source corresponding to the voltage, space vector modulation. Suppose if you are drawing all the voltage vectors, okay, then you can construct a hexagon. So here, okay, so you can construct, you can join here, then you can join here, then you can join this one, then you can join this one, then you can join this one, then you can join this one. See, so you are getting a hexagon. So in the hexagon shape, remember this will be representing your A phase, and this will be representing your B phase, D phase, and this will be representing your C phase. See how I have constructed that hexagon? Is that part clear? Is that part clear?
Yes.
Any doubt regarding the construction of the hexagon? Yeah, okay, fine. Okay, then so I will draw, see, I will draw the hexagon here once again. So you are having, you can take the 6 active vectors are there. So you can just draw the hexagon shape. Simply you can have like this. So you can have this shape. So you will be having, we can see is we will see this one. This is your A phase. I will mark this A phase like this. This is your A phase, and this is your B phase. You can mark like this. This is your B phase, and you can mark here. This is the C phase. I am just taking it out and radially out, and you can put it like this. So this is how you are having 1, 0, 0, and here you will be having 1, 1, 0, right? 1, 1, 0. Then here you will be having what? 0, 1, 0. If you have these 3 active vectors, then you can directly draw this one, because if it is 1, 0, 0, you can put, if it is 1 here, definitely this will be 0. If it is 0 here, definitely the opposite will be 1. If it is 0 here, definitely this will be 1. Clear? And if you are taking 1, not 0, if this is just opposite to this one, so definitely this will be equal to what? 0, 0, 1, because 1 you have to take 0, 1 you have to take 0, then you will be getting 1. And here also, if you are having 0, 1, 0, you will be getting it as what? 1, 0, 1. Just opposite to that one, you can put it, right? So here, so this is the construction of the hexagon in the case of a space vector modulation. So as you can see, you are having how many sectors will be there? You can see 1 sector here, 1 sector here, this one is another, this is another, this is another, this is another. So 6 sectors are there. So you have to mark that 6 sectors. So this is your first sector, this is second sector, third sector, fourth sector, fifth sector, and sixth sector. And remember, this each sector will be displaced at an angle of 60 degree. You can see this is 60 degree, right? 60 degree. And then you will be having, this is again 60 degree, this is 60 degree, this is 60 degree, this is 60 degree. Each one is 60 degree. And you are having 6 sectors are there. So totally you will be having 360 degrees there, right? 360 degrees there. So how we can say, because it will take 6 steps to complete one revolution. So one revolution means you are having 360 degree. So it will take 6 steps. This is the first step, second step, third step, 4, 5 and 6. So 6 into 60 degree you will be getting it as 360. So since it is taking 6 steps to complete one revolution 360 degree, we can call this type of inverter as a 6-step inverter. So remember, we can call this as a 6-step inverter. 6-step inverter because it takes 6 steps to complete one revolution. So this is a 6-step inverter. So and remember, you are having 6 sectors are there. These each sectors are displaced at an angle of 60 degrees. So each will be 60 degrees. So how we can represent? If you are having 0, 0, 0, if I am taking, then you are having 1, 0, 0, then you are having 1, 1, 0, then you are having then 0, 1, 0, then you will be having 0, 1, 1, then you will be having 0, 0, 1, then you will be having 0, 1, 0, 1. Again, it will be completing like this. So this one means you will be having at 0 level because at center it will be 0 level. In 1, 0, 0 means that is in this direction, right? So we can mark this as equal to VDC into e raised to j into n minus 1 into pi by 3, where n will be varying from 1 to 7. 1 to 7. And suppose if you are taking here, what you will be getting? If you are putting n is equal to 1, what you will be getting? E raised to 0, right? E raised to 0 is what? 1. So simply you are getting VDC value will be there. So VDC value means, as you can see, this is simply at 0 angle and it is having a magnitude VDC. That's okay, fine. If you are taking 1 on 0 and if you are putting this is equal to again VDC into e raised to j n minus 1. If you are putting 2 minus 1 into pi by 3, what you will be getting? You are getting it as equal to VDC into e raised to j pi by 3. What is pi by 3? Pi by 3 is 180 by 3. That's equal to 60, right? 60. So that means this 1 on 0 is displaced at an angle of 60 degree from 1, 0, 0. And similarly, you can put 0, 1, 0. The value is from 60 degree. Then again, you are having 60 degree. So the total of 120 degree phase displacement will be there. So if you are taking 1, 0, 0, you will be getting VDC and you have to put it as e raised to j into 3 minus 1 into pi by 3. So that is equal to VDC into e raised to j 2 pi by 3. So what is 2 pi by 3? 2 pi by 3 is 120. So again, this is 120 degree angle. As you can see, you can put like this up to 1 to 7. You will be getting the angle corresponding to this one. This is the way how you can take the displacement level in the case of a hexagon construction. Then, and one more point is there. As you can see here, if you are having this hexagon like this, we'll draw that hexagon once again. So if you are having a hexagon like this, then this hexagon will be, so this hexagon here you are having 1, 0, 1, 1, 1 or 1, 0, 0, 0. And the average variation of the voltage space vector will move along a circle with uniform velocity. See, you can see here, this is your A phase, this is your B phase, this is your C phase, see, and then the average variation of the voltage space vector, you are having 1, 2, 3, 4, 5, 6 voltage space vectors are there. So the average variation of the voltage space vector will always move along a circle with uniform velocity. See, that is nothing but you can have inside this hexagon, you will be having different circles possible. See, that will be inscribed by a different level circle. See, you can see different circles are possible. So the average variation, this is also another important point. So the average variation of the voltage space vector will move along a circle, with uniform velocity, Okay, so this is the most important thing in the case of a space vector hexagon. So the average variation of the voltage space vector will always move along a circle with uniform velocity. As you can see, inside you are having so many circles are possible. Okay. So how will you find out the maximum radii possible? So you are having so many circles are possible. So you have to definitely obtain a maximum radii corresponding to this one. So how it can be possible to have this maximum radii? So if you are taking this hexagon, the maximum radii means you will be having, it has to touch here, 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 and it has to touch here, it has to touch here. So if you are touch all these points joined together, you will get the maximum radii possible, right? Maximum radii. So I will draw once again. Okay. So you will be having, okay. So you will be having the maximum radii possible will be passing through all the points corresponding to this. You have to touch all the points here. Then you will be getting this point, this point, this point, this point, this point, and this point. Okay, you have to touch all the points. Okay, then you will be getting the maximum radii. So here, the maximum radii, this is your VDC, right? This is your VDC. Anyway, this is your VDC level. So that will be touching means you will be getting this total angle of 60 degree, right? Total angle in each sector is displaced by 60 degree. Okay, fine. Then what about the center? If you are having the center, if you are drawing a line like this, if you are drawing a line that is touching with this point, so this will be representing your VDC, okay, and it will be making an angle 30 degree. So what about the maximum radii possible in the case of a space vector modulation? Maximum radii possible? Anybody? Maximum radii possible? Maximum radii possible will be, since you are having 30 degree and you are having the magnitude as VDC, the horizontal direction you will be getting it as the maximum. So you will be getting the maximum, this will be VDC cos 30. VDC cos 30 will be the maximum radii possible. Or you can say, what is the value of this one? What is cos 30? VDC will do root 3 by 2. Cos 30 is nothing but root 3 by 2. So you can have root 3 by 2 into VDC. Or from that, in sinusoidal modulation also, you will be having a modulation index will be there. So how is it possible to have that modulation index level? So the modulation index means you have to take V reference by VDC, right? So the V reference means here you are getting the V reference as equal to VDC cos 30. So in the modulation index, if you are taking the modulation index, you will be getting M value, and that will be equal to M value, that will be equal to V reference by VDC, V reference by the maximum voltage. So that is equal to V reference. Now we are obtaining it as the maximum radii possible is VDC cos 30. So this VDC cos 30 divided by VDC, or you can simply write as equal to root 3 by 2, or that is equal to 0.866, right? 0.86. So the linear modulation range possible in the case of a space vector modulation is 0 less than or equal to M less than or equal to 0.866. Is that clear? So 0.866. So that is the case with the modulation index parameter in the case of a space vector modulation. And here, since you are having this, okay, since you are having this ABC structure, and this ABC structure and the balanced system, you can have this IA plus IB that is equal to minus IC possible. Again, we can have a flexibility of transforming this into the alpha beta structure. So if you are transforming this into the alpha beta structure, then you can simply take the reference vector. So in order to specify a reference voltage that is having a magnitude at phase, this voltage vector can be reconstructed on an average by using the 8 possible states of the system, right? So, 8 possible states which it is possible to have a reconstruction, and you can generate a reference vector. That is the aim. So, for that, what you have to do is you have to take an alpha beta structure. So, in alpha beta means if you are having a 3-phase system, that 3-phase system has to be converted to, this is your 3-phase system. This is your A, and this is your B, and this is your C. So this three-phase system has to be converted to a two-phase system. Two-phase system in the sense that should be an alpha beta, that is again a rotating plane, and that should be displaced at an angle of 90 degree. Why we are going for this one? To make the three-phase system analysis easier, in order to make it easier. And then what you have to do is you have to specify a reference voltage, right? So that reference voltage should be having a magnitude and phase, and this voltage vector you have to reconstruct on an average by using the 8 possible switching states. So you have to take sampling. So how you are doing this sampling means, in order to generate the reference voltage vector for a period of TS, sampling period, you have to do the reconstruction. So the reconstruction is done by sampling the reference voltage at a given period TS. So for that we are taking this three-phase system. This is the three-phase system to the two-phase system. So while you are converting from a three-phase system to the two-phase system, always make sure that the power remains the same. In the case of three-phase system, you are getting the power as equal to 3 VI cos phi. In the case of two-phase system, you are getting it as equal to VI cos phi, 2 VI cos phi. But here you are having cos phi. If you are taking it as unity, you will be getting simply, if it is a V phase and I phase, you are taking 3 VI. And here you will be getting the power in two phase as equal to 2 VI. But when you are converting from a three-phase to two-phase system, always you have to maintain the power invariance should be there. That means power should be same. Then the two power should be same. So for making that power same, either you can change the voltage or you can change the current. If you are changing the voltage, the constant magnitude, you have to always take 3/2 factor. 3/2 of V3 phase, and I you have to maintain the same as that of the three phase. Then you are, if you are changing in that way, the two-phase system voltage and the current, if you are changing with respect to the three-phase system, you are here, you are having three-phase quantity, you will be getting the three-phase power as such. So in order to maintain the power invariant structure, what you have to do is you have to change the parameter associated with the two-phase system into the parameter of the three-phase system. So you will be getting the same power, but you have to change either the voltage or the current level. So we will see what is then this I alpha from this one. Since we are taking the A phase and the alpha phase along the same direction, what will be your I alpha? What will be your I alpha? I alpha will be, since it is along the same axis IA, you will be getting it as equal to IA cos 0 plus IB cos 120 plus IC cos 240, right? So why? Because IA means along this direction. So you are having this alpha and A will be, or you can have the structure here itself. Then it will be more easier for you to understand. Beta, and you can have this one as alpha also, right? I am changing this three-phase quantity to two-phase quantity. So alpha axis and the beta axis are on the same direction. So I alpha current will be equal to IA cos 0 plus IB into cos 120 plus IC into cos 240, because you have to take all the horizontal component. Then here what you will be getting, IA into cos 0 is what? Cos 0 is, what is cos 0? 1. Sin 0, 0, cos 0, 1. Plus IB into, what is this one? Cos of 120. Cos of 120 means you can say 90 plus 30, right? Plus you have IC into cos of 180 plus 60. You will be getting 240, right? Then how you will be getting this value? Now I am moving on to the voltage boosting. How the voltage boosting is taking place in a space vector modulation when comparing with a sinusoidal pulse width modulation. That's why I am going like this structure. That means I am deriving all these points just to have the voltage boosting, how the voltage boosting is taking place in the case of a space vector modulation. So here you will be having IA itself. Then you will be having what? Plus IB. Then what about cos 90 plus 30? Cos 90 plus 30, if you are considering, you are having 4 quadrants are there. Cos, since it is an odd one, can write here as sine, right? And what about cos in the second quadrant? 90 plus 30 means it is in the second quadrant. Second quadrant sine is only positive. So here the component is cos. So definitely you will be having a negative sine 30 will be there, right? Plus you will be having IC, and again 180 plus 60. 180 means it is even number. So definitely it will be a cos 60 factor. But you have to take 190 plus 60 means this is your 190 plus 60 means in the third quadrant. In the third quadrant only tan is positive, cos is negative. So you can put a negative sign here. So you will be getting, this will be equal to IA minus IB into sine 30 is what? 1 by 2, right? 1 by 2. 1 by 2 minus you are having IC into what about cos 60? That is also 1 by 2, right? So you can write this I alpha value. So next one, you can write the heading as voltage boosting in the case of space vector modulation. Voltage boosting. Okay. So here you are having this parameter like this. Okay, parameter like this. Or you can write this will be equal to IA and minus 1 by 2 is common to all. So you will be getting IB plus IC. Right. But in the case of a balanced three-phase system, then you will be getting IA minus 1 by 2 into, what is this one? IA plus IB plus IC is equal to 0. Then what is IB plus IC? What is IB plus IC? That's equal to minus IA. So you can simply put here minus IA. Or you are getting it as equal to IA plus 1 by 2 IA. So what is that value? That is equal to 3 by 2 IA. Right, I alpha will be equal to 3 by 2 IA. Or the same way we can write the voltage also. V alpha will be equal to the same manner. You can write 3 by 2 VA. 3 by 2 VA. And in order to get the maximum voltage, you have to take the V alpha maximum. That's equal to VA maximum. So in order to compare with the voltage boosting level of sine pulse width modulation. So here you are getting V alpha maximum is equal to 3 by 2 VA maximum. Then what is V alpha maximum? That we have already written, that is equal to VDC cos 30. VDC cos 30, right? VDC cos 30 is what? That is the maximum radii possible corresponding to a space vector modulation, right? So you will be getting V alpha maximum is nothing but this is the maximum radii possible in the case of a hexagon. So it is VDC cos 30 into 3 by 2 into VA max. So find out the maximum value possible in the case of a three-phase quantity. So what is the value? Then VA max will be equal to 2 by 3 of VDC into cos 30 is root 3 by 2. So this 2 and 2 get cancelled. This root 3 and this will be cancelled. Finally, you will be getting it as VDC by root 3 only. Okay, VDC by root 3 only. That is equal to 0.577 VDC. 0.577 VDC. So in the case of space vector modulation, you will be getting the maximum value of the A phase. The maximum value of the A phase voltage will be 0.577 VDC. But in the case of sinusoidal pulse width modulation, if you are taking sinusoidal pulse width modulation, you will be getting this maximum value of A will be equal to VA max will be, you will be getting just half, that is 0.5 VDC. So here you have to prove it, how you are getting this 0.577 VDC. So VA max will be, in the case of sinusoidal pulse width modulation, it is only 0.5 VDC. So from this proof, it is clear that this space vector modulation will be having a voltage boosting up to 15%. If you are taking 0.577 divided by 0.5 into 100, you will be getting it as 15% voltage boosting will be taking place in the case of a space vector modulation. Voltage boost will be taking place in the case of SVM. Is that clear? Is that part clear? Okay. Then we will be moving on to the generation of pulses. That's also very, very, very important, generation of pulses. So just I will move on to the generation of pulses. Rosalind, can I continue? Rosalind?
Okay, Miss, continue.
Okay then. Okay, thank you very much. I will anyway. I will complete it soon. So you will be having this. What you will be moving on to the generation of pulses. Okay, just write the generation of pulses. So first of all, we will see the switching period or the dull time. Switching period, switching period. Next, you write the heading as switching period, or you can say dull time, or you can say sub-interval level, sub-interval, sub-interval. Okay, sub-interval level. Okay, we will move on to this one. So what do you mean by this switching period? Now we have the two axes will be there, as you know, the three-phase quantity. Now we are transforming to the two-phase quantity level. You will be having two axes will be there, one along beta alpha, one along beta. Alpha and beta are at 90-degree apart. So, okay. Then you will be having two vectors will be there. So if you are taking the first sector, so if you are constructing the first sector, in the first sector you are having what? 1 0 0 is there, then you are having 1 1 0 is there, then here you will be having 1 1 1 will be there, then you will be having 0 0 will be there. The angle between these two will be 60-degree, and this will be representing your first sector, right? First sector. Then, so here I am taking the first sector. So I am moving on to the sector 1. Sector 1. Rest I will give you as assignment, or you can do it by yourself. I will take only the sector 1. So the sector 1. So in the case of sector 1, you will be having a voltage V1 will be there, and let that voltage V1 be switching for a period T1. Okay, and then you will be having, this will be representing your 100, definitely 100. And then you will be having another voltage that will be, because it is 60-degree, the total is 90-degree, but you have to take 60-degree angle. So you will be getting at 60-degree angle, you will be having V2, and this V2 will be, that is 110, and this is switching for a period T2. This is switching for a period T1. So you have V1 that is switching for a period T1, then V2 that is switching for a period T2. Then you will be having, you have to take the voltage reference vector. So the voltage reference vector, I told you, by specifying a reference voltage, that means having a magnitude and phase, a voltage vector can be reconstructed on an average by using the 8 possible states of the converter. So the reconstruction is done by sampling the reference vector. So if you are sampling the reference voltage at a given period Ts, if you are sampling it for a given period Ts with a sampling frequency, having a high sampling frequency, then this space vector transformation can be used to analyze these electric systems. So now you have to consider the reference vector. The reference vector should be the sampled reference vector, or you can say, what do you mean by the sampling means? If you are taking this reference hexagon phase structure, if you are taking this hexagon phase structure, then you can sample means nothing but you will be having a, inside this hexagon, you will be having a circle. You can have different circles will be there, and you can take one reference vector, let this be Vs. You can sample means you can sample at this point, or you can sample at this point, or you can sample at this point. You can sample this Vs at any point. So there will be a small jump between the two sampling points. Okay, there will be a small jump will be there in between the sampling point. And remember, in order to reduce the switching losses also, this sampling is necessary. So we are moving on to this V reference vector. So how we can have this V reference vector? This V reference vector should be like this, or you can call this V reference, or you can have this as Vs, sampling vector. So you can take it as Vs, and this Vs will be switching for a period of Ts. So this will be making an angle alpha. So remember, this will be making an angle alpha. Then how we can generate the pulses corresponding to this one? So how we can generate the pulses corresponding to this sector 1? So you are having a sector 1 like this, and you have to generate the pulses corresponding to this one also. So this Ts, this total sampling time, that will be equal to, you are having T1, that is this V1 is switching for a period T1, plus you will be having T2 is switching for a period, V2 is switching for a period T2, Then in addition to that one, in that particular sector, you will be having two zero states are there, 1, 1, 1 and 0, 0, 0. So this is your V1, this is your V2, and this is your V0 because it is representing a voltage. So you are having a two zero state voltages are there. So that will be switching for a period. Even though it doesn't appear in the output voltage, you have to put it that as equal to T0 because you have to take that order. Then only you will be getting the full sector. So in order to get a full sector or the first sector, you have to take this point also. Then only you can close it, right? So you will be having 0, 0, 0, then 1, 0, 0, 1, 1, 0, then 1, 1, 1. Then it will be a complete path. So you will be having Ts will be equal to T1 plus T2 plus T0. Then our ultimate aim is to obtain the values corresponding to this T1 and T2. So how we are attaining this one? So for that, you have to take the volt second balancing. So volt second balancing. Volt second balancing. So what do you mean by volt second balancing? Volt second balancing means we are having V alpha and V beta here also, right? As the axis. You are having V1, V2, Vs and the zero vectors are there. So you have to take the horizontal component along this alpha axis. You have to consider the vertical component also. So if you are considering the horizontal component, how we can represent this one? If you are taking the horizontal component, so you are having volt second means you have to multiply the voltage with the time. Okay, voltage with the time. So how you can represent this volt second balancing in the alpha axis? So if you are considering alpha axis, as you can see in the alpha axis, you are having a voltage and that is switching for a period T1. So volt second means you have to multiply this V1 with T1. So I am just multiplying with V1 into T1, right? V1 into T1, 5 plus. If you are taking V2 in the first sector, and I am making an angle 60 degree with V1. So or it is displaced from the alpha axis by an angle 60 degree. So you can have V2 is there, that is switching for a period T2. So you will be having V2, T2 is there. Then what about this one? The horizontal component will be cos 60. So you can take V2 cos 60 into T2. Okay, that is along alpha axis. Then that will be equal to what? That has to be equated to what? You are having the sampling voltage Vs and that is switching for the sampling time Ts, and that will be making an alpha angle with alpha axis, right? So you can have, this will be, if you want, you can have the modulate because it will be having both voltage, magnitude and phase. So you can simply take the magnitude of this one, Vs, and it is for Ts, and then you will be having cos alpha. Cos alpha. This is corresponding to the alpha axis equation. Then corresponding to the beta axis, you have to take the vertical component. What is the vertical component of this one? V1 is not having any vertical component because it is along the alpha axis. So no vertical component will be there for this V1 T1. So you can take 0 plus, what about this vertical component corresponding to V2 T2? Since it is making an angle 60 degree, definitely you will be having V2 sin 60 into T2. So you can have V2 sin 60 into T2. So that will be equal to, you will be having Vs Ts is also making an angle alpha. So it will be definitely having a vertical component. So that is equal to Vs Ts into, then what? Sin alpha. Vs Ts into sin alpha, right? But we know that this V1 and V2 is nothing but that will be always representing the maximum value that will be equal to V1 and V2 will be equal to nothing but the VDC because the hexagon, the maximum value possible is VDC. Simply we are writing it as equal to V1 and V2 just to represent 100 and 110. So you are getting V1 and V2 as equal to VDC. So here we can represent VDC itself, or no need to write this V1 and V2. I am just for this clarification, I am writing it as V1 and V2. You can put that value as equal to VDC itself. Then from this you have to find out the T1 and T2. So the switching time corresponding to V1 and switching time corresponding to V2. So first you have to find out T2 from this expression and substitute in this first expression. And then obtain this T1 value. Then we will generate the pulses. Okay. Then I will say how to generate the pulses. So this is your first equation. Let this be your second equation. From the second equation, Write the value corresponding to T2. So what is the value corresponding to T2? You will be having Vs, then you will be having Ts, then you will be having what? V2, or you can write as equal to VDC. I am just writing it as equal to V2 into sine alpha divided by sine 60. Okay, sine alpha divided by sine 60. Or I can simply write this will be equal to Vs into Ts divided by VDC, because V2 is the same as VDC. So into sine alpha by sine 60. Sine alpha by sine 60. This is your T2. Then this expression you have to substitute here and rearrange. Finally, you will be getting T1 value. So if you are substituting here, then what you will be getting? So you are having V1. I will take another color. So you will be having V1 T1, right? Plus you will be having V2 into cos 60. Okay, fine. Cos 60. Then you have to write this will be equal to Vs into Ts into sine alpha divided by VDC into sine 60, right? Sine 60. So this will be equal to your Vs Ts into cos alpha, right? As you can see here, this is your VDC. I have taken this V2 as equal to VDC. In similar way, you can take this V2 as equal to what? V2 is the same as VDC. So you can put here as VDC itself, because this is VDC. And here also you can put this V1 as equal to what? VDC. Because you are having V1 and V2 is the same as the maximum value VDC. So VDC is equal to this one. Then you can rearrange, because you are having VSTS here. Here also you are having VSTS here. Just to rearrange this VDC and this VDC will cancel. So just to rearrange and find out this VDC into T. So VDC into T1, that will be equal to, you have Vs into Ts. Then you will be having, here you will be having cos alpha. Then you can write cos alpha. Minus here you will be having sine alpha, cos 60 is there. Definitely you can rearrange this as sine alpha into cos 60 divided by, you will be having sine 60 is there. Sine 60 is there, right? Then what is this cos alpha sine 60 minus sine alpha cos 60? What is sine A minus B? Any idea? Trigonometric expression? I couldn't see all of you. That's why I don't have whether you are understanding or not. I don't have any idea. So Vs into Ts, right? Into, you can just simply multiply. This is cos alpha into sine 60 minus sine alpha into cos 60. Cos 60. Okay. That divided by sine 60. So what is this value? What is this value? This is equal to Vs into Ts into, what is this one? This is cos A sine B minus sine A cos B. So we can write this will be equal to sine 60 minus alpha, sine A minus B, 60 minus alpha. That divided by sine 60. Okay, sine 60. So you have the expression for this T1. So what is T1? In the case of first sector, the expression for T1 is Vs. Then you have Ts divided by VDC, right? So you can put it as VDC into sine 60 minus alpha, because alpha is the angle with which the sampling vector makes with the alpha axis, divided by sine 60. So this is the expression for T1 and this is the expression for T2. This is the expression for T2. Let it be 3 and let it be 4. Okay, let it be 3 and 4. Okay, so this is the case. Now you have to draw the generating pulses for sector 1. That is the last part. Okay, I will quickly finish it. Generating pulses. So next you write generating pulses. Generating pulses. pulses. So you can draw it by yourself. Okay, I will just give you an idea. So here, since you are having in the sector, you are having 1 0 0, then you will be having what here? You will be having 1 1 0, then you will be having 0 0 0, then you will be having 1 1 1. Then what you have to do is you have to take this zero switching period has to be divided into two parts. So this T0 has to be divided into T0 by 2 and T0 by 2. Then if you are making an 8 switching circle, so see, first of all you are starting from 0 0 0. Make sure that the number of switching should be less. So 0 0 0 I am starting from here. Then the next one I am taking it as equal to 1 0 0. See, 1 0 0. So as you can see, 0 is switching to 1, this 0 as such, this 0 as such. So one switching state will be changing, right? So the switching pattern, you can see only one switching is taking place here. Now you have to take 1 0 0. Now you have to take 1 1 0. So here also you can see 1 as remains the same, but this 0 is changing to 1 and 0 remains this one. So again one switching is taking place here. Then you will be having 1 1 1. Okay, so this will be forming your first sampling period TS. This is first sampling period, or you can call it as the positive sequence. Positive sequence. This is your positive sequence. Okay. Then similarly, you will be having a negative sequence will be there. So the negative sequence will be how you have to move is you have to take this 1 on 1 as such, because it will be the shortest one. Okay, T0 by 2 will be there. Then you have to take one switching has to be taken place. So that means here you have to place 1 on 0. Then you have to place what? 1 0 0. Then you have to place what? You have to close it, right? So you will be having 0 0 0. Then this will be forming your negative sequence, or the uh, second sampling period. Okay. Then you have to draw the waveforms corresponding to sector 1. Waveforms corresponding to sector 1. See, you will be having, you have to draw like this. You have to draw like this, all the first sampling and the second sampling together. Then you have to draw VS0, VB0 and VC0. So how is it possible to have VS0, VB0 and VC0 for the sector 1? So here what you have to do is you have to take, see, you have to take VS0. You need VS0, right? VS0. So I am drawing VS0. VA0 average. VA0 average. I have to draw VA0 average. I have to draw VB0 average. Draw VC0 average. This is also most important in the case of space vector modulation, how you are generating pulses. So if I am taking this as your reference, and now I am taking this VDC, I am splitting and I am taking it as equal to, instead of 0 and VDC, I am taking this as equal to plus VDC by 2 and minus VDC by 2. So this is VDC by 2 level and this is also VDC by 2 level. Or you can have the structure like this. You will be having the structure like this. Okay, you will be having the structure like this. Okay, then this is the midpoint. So you can take plus VDC and minus VDC by. So here, see, A voltage you have to draw. So here A is 0 and here only you will be having A1, 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 A1. So you will be getting a voltage. This voltage will be, here you will be getting minus VDC by 2. Then you will be having up to this point to this point you will be getting the plus sign. Then you will be getting minus VDC. So this is the generation of the sector waveform, VA0 waveform corresponding to the space vector. So for sector 1, VA0 will be like this. So this is your plus minus VDC by 2 and this. So you are having VA0 average is there. Similarly, you have to draw VB0 average. How will you draw the VB0 average? VB0 average, as you can see here, here the second one is there, here one, second phase, one, second phase, one, second phase. So up to this level, you will be getting the maximum value, V phase, and then you will be getting the minus VDC level. So can you draw this one? Okay, so I will draw VB0 average also. So VB0 average means VB0 average means, see, this is your reference. From that reference up to this level, your V phase is 0. So you can have up to this level, you will be having VB0 0. Then when you are starting from here, you will be having the second phase as 1, 1, 1 and 1. So you can have up to this level 1, 1, 1. Again in the second phase, you are having 0, 0. So you can just draw like this. And this will be representing the VB0 average corresponding to sector 1. Then how will you draw, or like how will you generate the three phase, I mean VC0 average, again VC0 average, you have to take the C phase as 1. So here you have to mark this is equal to your reference. Then as you can see, the C phase will be maximum only when in the center point, right? So you can see here, you will be having the maximum point will be equal to here 0, 0, 0, and here you will be getting 1 and 1. So up to this level, it is 0. Then you will be having maximum 1. Then these 2 points you will be getting maximum. Then it will be negative because all the points you are hitting 0, 0, 0 in the C phase. So this is your VC0 average corresponding to sector 1. VC0 average. So VC0, the equation for if you are having this generation pulses and the equations corresponding to sector 1, then it will be easy for you to draw the other sector waveforms. It's very simple to have this waveform structure. So we will see how this voltage equation you have to derive. So with that I will conclude. Okay. Then you have to get this VA0 average. So what is VA0 average? So this VA0 average, that will be for a sampling period TS, right? That is for a sampling period TS. As you can see here, this is what? This is your VDC by 2. This is your plus VDC by 2, right? VDC by 2. So common, you are having a VDC by 2 factor will be there. Then you have to take, okay, so then you have VA0 average, you have to find it out. VA0 average, right? So that is equal into TS, that is equal to, you are getting it as equal to VDC by 2, right? VDC by 2 into, you are having what? Minus T0 by 2 is there. In that plus T1 level, you will be having a positive 1. Plus T2 level, you will be having a positive 1. Plus T0 by 2 level, again you will be having a positive 1, right? So you are having a waveform like this. So see here, then you will be having like this. So at this level, you will be having minus T0 by 2 level. Then you will be having T1, then you will be having T2, then you will be having T0 by 2. Then it will be repeating. So you have to like this. Then you have to cancel these two parts because T0 will not contribute to the output voltage. So finally, you will be getting VA0 average. That will be equal to VDC by 2 into you are having T1 plus T2. Okay, T1 plus T2 divided by you are having TS. That is the expression. Similarly, you have to write for VB0 average. So what is VB0 average? VB0 average into TS, you are getting it as equal to VDC by 2. In that figure, you can just represent, you can just look at the figure, then you can write it. So here you will be having minus T0 by 2 is there. Then you will be having minus T1. As you can see here, the waveform will be up to this level and then it will be starting. So you will be having two levels. This is minus T0 by 2 and this is minus T1. And then you will be having T2 and T0 by 2. Okay. So this is your VB0 average and this is your VA0 average. Okay. Then minus T0 by 2 minus T1. Then you will be having plus T2 will be there. Then you will be having plus T0 by 2 will be there. Again, here you can cancel these two. Finally, you will be getting VDC by 2 will be into. Then you will be having minus T1 plus T2 will be the equation corresponding to VB0 average. Okay. Or we can write VB0 average will be equal to this VDC by 2 into minus T1 plus T2 divided by Ts. Similarly, you can write VC0 average. So VC0 average means how you are getting this VC0 average. VC0 average means you can look into the waveforms. So VC0 average, that will be equal to into Ts, that will be equal to simply 111 and 111, right? So you will be having 111 and 111 only you will be having. So three factors will be there. Minus T0 by 2 minus T1 minus T2 will be here. So you can have VDC by 2 into minus T0 by 2 minus T1 minus T2 then plus T0 by 2. Again, this will be cancelled. Can have VDC by 2 into minus T1 minus T2, that is equal to VC0 average, the whole divided by Ts. Or if you are taking minus sign outside, you can simply write as equal to minus VA0 average itself. You have to take minus, because in a balanced three-phase system, VA0 plus VB0 plus VC0 will be equal to 0. So you will be getting, if you are taking this one, VC0 will be equal to minus VA0 itself. So the next sector, I won't derive any expression corresponding to that one. I will just show you how the pulses can be generated from this one. And the rest of the sector, you can do it by yourself and you just try it. And if you have any doubt, you can contact me at any time. Okay. For sector 2 also, I will generate the pulses. Sector 2. Can anyone generate the pulses corresponding to sector 2? If you are having a sector 2, in the sector 2, this is your sector 1 and this is your sector 2. So here 0, 0, 0, this is 1, 1, 1, this is 1, 0, 0, this is 1, 1, 0. And what about here? Can anyone say what is this one? 0, 1, 0. So this is your sector 2. Right. So how you will draw this one? In the sector 2, you will be having 0, 0, 0. Then you will be having, you have to take 0, 1, 0. Why? Because you have to take this one. Instead of 1, 0, 0, you are having only one switching is possible. So in order to reduce the switching losses, you should be having a single switching pattern is there. So you have to take 0, 1, 0 in the second segment. Then you will be having 1, 1, 0. Then you will be having 1, 1, 1. Then 1, 1, 1. Then similar way, you have to just reverse it. 1, 1, 0. Then only you will be getting the switching losses less. So 0, 1, 0. Then you will be having 0, 0, 0. Right? Then this will be your positive sequence. This will be your negative sequence. How your VS0 will be coming in the sector 2? What about the VS0? Can anyone say? What about VS0? If you are taking VS0, this is your reference. This is your reference. So if you are taking VS0 average for the sector 2, VS0 average, sector 2 means, as you can see, here you will be having 0, 0, 0. This is 0, 1, 0. So the sector 2 means A is here, right? So you can have this one. So you, up to this level, you will be having, up to this level, you will be having the negative, and the sector 2 VA0 is positive only up to this level. So you can take this one and you will be getting like this. This is your VA0. What about your VB0? What about your VB0? VB0 means you are having the second phase should be 1. So all these have second phases 1. So you can have a structure like this. Can have a structure like this. So this case is with you are having this is 1, this is 1, this is 1, this is 1. And now you have to take the C phase. So if you are considering the C phase, how you will be getting the VC0 voltage, VC0 average? How you are going to get this VC0 average? So this VC0 average means you are having, so you have to generate the pulses. This is also very important. So VC0 average, see, C should be 1. So this is 1, this is 1. That is the only thing. So what you have to do is you can have up to this level negative, then you will be having positive, then you will be having negative. So this is your VC0 level. Then you have to write the equation also. The equation means you are having VA0 average into TS, that will be equal to VDC by 2 into what you are getting. As you can see here, minus T0 by 2 minus T1 plus T2, then T0 by 2. So you can take this one. That is minus T0 by 2 minus T1 plus T2, then plus T0 by 2. And similarly, VB0 average also, you can write the expression. What is this one? VDC by 2, you can have simply minus T0 by 2, right? So this is minus T0 by 2. This is plus T1 plus T2 plus T0 by 2. So you can have minus T0 by 2 plus T1 plus T2 plus T0 by 2. What about VC0 average? That's equal to VDC by 2 into, you are having minus T0 by 2 minus T1 minus T2 only plus T0 by 2. So minus T0 by 2 minus T1 minus T2 plus T0 by 2. So like this, you can have the generation of pulses in the other sectors also. You just try for sector 3, 4, 5 and 6, and then write the equations corresponding to that one and find out the VA0 average, VB0 average and VC0 average. Then if you have any doubt regarding this one, you can ask now.